So thanks for the introduction. So after we now have heard that the energy transition is basically impossible and will ruin everything, I will now spend the next 45 minutes just to approach the issue from the complete other direction. So let's just assume we want to do the energy transition, so that means decarbonizing the power sector. And instead of like asking which current operations or construction principles are violated by a possible shift, how could a possible solution just look like? So, and maybe we can derive some insights from that. But just to be clear, I'm not presenting anything that is a pathway towards a future energy systems. I'm presenting our research that is just considering how they might look like. And so for the first 10 slides, I will basically be spending only on explaining how we came to those results. Because in essence, if you understand how we come there, then you can see that's basically just a question of our assumptions and our decisions, which kind of system we want to have in the future. And not so much about what our method is. So, let me just give you a short background on myself. So I'm an electrical engineer by training. I studied at the Technical University of Munich and did my diploma at an Institute for Energy Economy on the renewable supply of a fuel cell vehicle fuel station. And then I started my PhD there and moved to the Institute for Renewable and Sustainable Energy Systems while staying with the same professor, Professor Hamacher. And our institute now, broadly speaking, can be summarized with a circle diagram on the right. So generally, we model or optimize possible future energy systems, and we consider, of course, renewables, the problem of storage, the problem of energy transmission between different locations and sectors, and where actually the power or the energy is generated. So this is basically a key paragraph. We have technology-focused system models. That means we take our engineering training and respect the basic premises of what a power plant or an energy conversion can do, but depending on the study I'm presenting you, only very basic constraints are satisfied. So for example, in all of the results you're going to see there's no ramping constraints for power plants implemented. While this is possible, this is not done here for simplicity's sake. And we still think the results have some validity, but not validity in a sense that you can really build it like it is shown. So always bear in mind, we're looking at visionary stuff, and it's just informing maybe a possible pathway. And so I think I have disclaimed enough. They actually can now go to the meat. So as I already said, I will explain how we do optimization. What do I mean by that? What do I mean by optimal planning and operation of technical infrastructure? Because we're both considering here the construction of capacities. That means generation, transmission, and storage. And also its commitment. Here in this talk, I'm always using a 1 hour time step resolution. But from the method, you also could go down to 1 minute. So again, for simplicity's sake and for traceability of models, it's at 1 hour. Then I will present the results of 3 optimization studies we did during the last years. And then in the end, I will go to the limits of what we cannot or can derive from those results for our current situation. So our optimization models, or many of the models we have heard about, they were all only considering time series or data curves. And implicitly, we're always assuming that space is concentrated in a single point, that energy can be exchanged. So in some of the models we also use this assumption, but we make it explicit by really visualizing as something as a point. For example, in Germany, we always say very often in modeling circuits, it's that Germany is a copper plate, and by that they just mean energy can be just transferred from any point to any other point. And actually, that's how the energy market or the power market in Germany is organized legally. So any offer can be made at any point in Germany without considering whether there's actually a physical link that is capable of transmitting the energy. So then if you're doing it more advanced, you of course always arrive at something like a graph structure, which just covers the link information, like how well connected is a certain location here, as the example of a small town in Germany, or here, very, very stylized, painted, how the countries in Europe and Northern Africa are or might be linked. So these graphs either represent existing or the possibility for transmission capacities. So for example, here France might be modeled as a point, but linked towards, for example, North Africa, which will become important at a later result I'm going to show, goes through several regions. Yeah, as I've covered space, time, as I said, we're covering it here with a 1-hour time resolution. And here you can see, just for a random location in Bavaria, the annual capacity factor time series for a potential photovoltaic plant and a wind turbine. And in the shaded area shows the minimum and the maximum daily value. Of course, for PV, there's this 0 because there's always a night. The thick line is the mean value of each day. Here you can clearly see the seasonality. Whereas for wind, you see, wind conditions don't change so dramatically over one day, but they can stay pretty bad, as in close to 0 for extended periods of time, several weeks. So purely local renewable energy supply looks very challenging, or is very challenging, which you already can tell from that. And our models very much rely on plenty of those. So for each location, if you now visualize Europe, you can have, and we actually used like 39 locations, all representing a country or a large region, and every region has 2 of those curves for a full year. Then how do we model technology, or all the processes, or all the built-up stuff? Basically, in each of the nodes, in each of the regions, you can conceptualize such a box, which basically uses the reference energy system nomenclature that's been around in the power engineering sector since the 70s. And on the right side, you see the demand, also represented by a curve similar to the capacity factors I've shown you on the previous slide. The supply here, for example, for wind is exactly the time series I've shown you before. Then there could also be other supplies that are available at will, like gas, for example, which you can store at reasonable quantities. Other commodities are like coal, uranium, which all can be added to this graph. In the middle, you have all the commodities, we call them, all the energy carriers or fuel types or intermediary, or also final products from these processes. And each technology type can be just aggregated to a box that consists of an energy flow into it, of one or several fuels, and one or several output products. And each of those boxes is just characterized by its capacity, its efficiency for each input and output, and then you can also associate investment costs, fixed maintenance costs, and variable costs for the operation of such a technology. So these are just random labels, and in the actual studies we're doing, those graphs are actually a bit bigger, but I've omitted most of the detail here. Then some commodities can also have storage. Those also just are basically black boxes which have a certain cost for building them, another cost for operating them, and their function is just to store a certain commodity at one time and release it at another time. So having all these preliminaries out of the way or in place, how do we actually model the thing? And mathematically speaking, that's everything. So I should probably explain what the vectors are. So x is basically everything we want our system to consist of. Like every capacity of every process I've just shown you on the previous slides, and there are actually hundreds and thousands of those scattered around your study area. And the operation point of each of those plants at every point in time is also a variable. And then this vector here just are the cost factors for each of those variables. So for example, a nuclear power plant might have, just making a number up, like 4,000 or 5,000 euro per kilowatt. Then an entry that corresponds to the capacity of a power plant at a certain point in the graph has just a prefactor of 5,000 here. So actually, when you're going to real size power systems, you're getting up to very large numbers of variables. Why are we doing it? Then the second equation here basically then just covers all the rest, which means it assures that the sum of production of all the plants that are actually installed satisfy the demand that we have just assumed to be fixed. It also assures that if you want to use a certain technology, that the capacity must be installed and via this equation also be paid for. So while this looks quite simplistic, by using large numbers of equations, you can also already be very, very advanced in what kind of problems you can model with it. And the challenge then doesn't lie anymore in the actual formulation, but in managing your assumptions, because the amount of assumptions in those matrices are huge. And actually, in practical work, we never see this representation directly. This is fortunately now handled by standard software for us. Yes?
How do you connect the graphs with your optimization formulation here? Do you assume that each power plant is already located in a specific space location? I don't have the connection between the special issues and the production generation issues.
It's actually we are. If you assume that the gray box around here represents a country, then such a gray box, which might be labeled nuclear, would represent the whole fleet of nuclear power plants in that country.
So you don't have any network information?
Within that region, no. And if I wanted to make a national study, I would basically split up France into 20, 50, 100 single vertices and then cover that.
Then how do you connect the splitted region to the
The splitted regions, this is omitted here. This is basically covered by, here I must provide the graph of all possible connections. Actually, those connections again are, you can conceptualize them also as a process box which has a certain capacity, which either can be chosen, which is then part of this variable, or you can just say they're connected. So I'm still not at the. Yes. So if I want to increase the resolution, I just have to increase the number of nodes. But in this, but actually a colleague who is finishing his PhD right now, he's doing this with, I think, 600 nodes for Europe. So there he goes to the regional level, but it's not ready yet, so I cannot show these results. So for the sake of simplicity also, I cannot go into all the scales. I just want to give you a feeling of what you can do and what you cannot do with these models. Actually, they come from the domain of operations research and have been used for huge domain or large domain of stuff. And here we are just using them for power or energy systems. One more theoretical slide, because because you might think that linear formulations are very limited, and yes, in a way they are, because they only can capture so-called convex problems, which means they always go for the cheapest solution first. So if by parameterizing the previous problem and say, give me the cheapest solution for European power system, it always just goes for the cheapest solution first, which might, for example, be wind in Spain, just let's assume. And it uses it up until the capacity that I have allowed it to use is exhausted, and then it moves to the second cheapest solution, which is kind of not how we would plan it in the real world. We would rather have some kind of economics of scale that stuff becomes better or worse the more you use it. And to capture that, you would need to introduce that some of your variables are integers instead of continuous variables. And if you allow for that, unfortunately, the problems become much more difficult to solve. But instead of just having linear costs, this is the CTX from before, which basically only can capture any costs that scale linearly with your variable. This is just one possible variable, like the capacity of this power plant I spoke before. And if you introduce integer variables, you can have something like this. And this basically means that the specific costs for a certain technology can be lower if you have larger capacities of it. But yeah, I think I'll skip that and move to the preparatory slide for the results. So I will give you the result of 3 studies we did on different scales. I started at the local scale of 20 smart buildings, then moved to the national scale, and in the end moved to the international scale. So for all those, basically the energy transition is just assumed to be set. We're in the future and we have decarbonized the power system to a large degree. And then the question is how we can use intermittent sources to cover the demand. And in terms of demand, we are just assuming that current levels of electricity demand continue in the future, because there are lots of trends which say they will grow. Other trends say they will fall. And as we are going into the far future anyway, we just assume today's power requirements. So the first study. Assume we have 20 smart buildings, and each of them has a pretty fancy energy system. Again, these are the boxes I was talking before. So these just show the availability of technology, not their size. Those will be determined now by the optimization itself. So the consumer has 2 types of demand, electricity and heat, represented by an annual time series. They can use either local sun, the electricity grid, or some gas, which can be burned in a CHP locally, which then produces both heat and electricity, or use PV, which only produces electricity. Maybe use some excess electricity for electric heating, possibly install heat storage and a local battery, and this happens in every building. And the question now that was asked by my colleague was, what degree of autonomy could such a building feasibly achieve? And on the left, you see the results only in case you have PV, no CHP. CHP, combined heat and power, sorry, acronyms. And on the right, also if you have photovoltaics and PV. And here you see on the x-axis the amount of PV that is installed on the smart building's roof, from 0 to 10 kilowatt. And here on the y-axis, you see the degree of energy autonomy that building could achieve. And in blue, you see PV without battery, and in red with a very reasonably sized 3 kilowatt hour battery, so actually pretty small. And you see that the attainable autonomy does not exceed 0.6 for an individual building. And that even here in these other lines which are dashed show that if the buildings cooperate, that they pool basically their storage, that they cannot really move up much in terms of their autonomy. So on a local scale, basically, without giant capacities, they are basically screwed. But here we found, or he found, that if you add CHP, which just is basically another degree of freedom in providing local energy, you can go very high in your energy autonomy, which is actually not true, as you then rely on bought gas and basically use gas as a flexible way of providing local electricity.
But when you add CHP, then you also make sure that indeed the heat is used or heat is available when necessary.
Yes.
It's not something which you smear out, but you use it when necessary.
Yeah, the heat was.
Winter, summer, different, and so on.
Yeah. So in that case, the CHP and the PV basically synergize perfectly, because in the summer you get more electricity from PV, and in winter you can use electricity basically as a byproduct from heating, which you then do anyway. So in that way, some synergies could be found. And this is also one of our main trajectories right now, that coupling heat sector and electricity sector might be one of those hidden, not low-hanging fruits, but medium-hanging fruits, where we still might get some potential for future optimizations. Yeah.
Sorry, I have difficulty to understand how you can get 40% of autonomy with PV alone, knowing that the PV capacity factor is around 10%.
Yep. I think there I'm reaching the end of what I can basically answer on the fly. But we can look up the numbers. I have the paper open here, but I think it just would cost too much time to. But I'm quite sure the numbers fit. So let's move on to the national scale. So here basically the problem to be solved is quite similar to the previous talk, and numbers also match in the result. The question asked here was, this is the PhD thesis by a colleague, finished in 2012, and the question was energy transition. We're in 2050. Here is plotted the residual load duration curve, which means basically the power demand of Germany minus the intermittent renewable power feed-in at the time, and sorted descending. So this is basically 2010. We have always at least something over 20 gigawatts to be covered by conventional power plants. Whereas if we assume a scaling up of intermittent renewable supply, the green curve emerges, and there we have a large share of, these are the surpluses, which were mentioned earlier, and a much more unattractive triangle to be covered by conventional power plants. And if we now assume that Germany has to do it basically all on its own and cannot rely, due to the strong coupling between its neighbors, for covering the gaps, how would storage have to be built up? And here you can see basically the result that was derived from a time series analysis. Here down you can see pumped hydro storage as we have it today. And here the blue area is basically the cheapest technology that was included in this thesis, hydrogen storage, which basically uses electrolyzers and then later gas turbines to burn the hydrogen with a not so good round-trip efficiency. And here,
Sorry, then you use fuel cells or gas to power?
gas.
Power to gas.
Gas? No, just burning the hydrogen.
Okay.
So really the round-trip efficiency was not so high. Again, I don't want to tell you the wrong numbers, but it was, I think, below 50%. I think it got to something like 30, but yeah, don't. He did the numbers. And here in between you see a small wedge of adiabatic compressed air storage, which just is used because it was assumed that there's no additional capacity for pumped hydro storage, which would have been a much more unattractive of course, the cheaper option, but as environmental concerns are an issue in Germany, and also topography is an issue, there was not so much potential for more growth in that technology. And just for added visuals, here you can see how in that study the storages were used. Pumped storage, like today, basically was a day-night operation cycle. So here you can see the filling status of those aggregated storages. The compressed air storage basically, I would say, flattens out the wind stochastics, and hydrogen is just used for seasonality. And even with that, full renewable integration was not possible. So still there was a surplus, even with those giant capacities. Maybe you've seen it as like close to 4 terawatt hours. So it's in the single percent digit fraction of the annual demand. And one problem, of course, with such a study, it's very sensitive to the actual time series that you use both for demand and for the renewable fluctuations. So depending on the actual time series he used, he entered, I think, over 10 different weather years, the optimal power storage or energy storage capacities varied from 3 terawatt hours to over 22. But this is just a result from those strict constraints that you have to basically be fully renewable within Germany without any help. And then you get such high degrees of variation.
What is the proportion that you get, the percentage that you get? Food integration, you say is not achievable, but how much can you?
Depends on the scenario. It's basically, you can get any number in case, as it is very fabricated, and he investigated like 12 scenarios. I can give you too many numbers to, so probably you wouldn't build it anyway like that. So the last result, now we're going from the country to continent scale, and we're not keeping it at Europe. We're also integrating North Africa and Middle East. And this was a study we did for the Desertec Industrial Initiative in 2012 or 11, and we were allowed to publish a report on that work in 2012. And there, basically, we just assumed we want a cost minimal power generation system for those 39 regions. So some countries were split into several regions because the transmission links would become very important in the solution we obtained. So we wanted to be sure that we capture where the main interconnectors between countries are. And we wanted to achieve a 95% reduction of CO2 emissions compared to today's level, basically meet climate reduction goal, greenhouse gas reduction goals, not climate reduction. So here you can see the graph that we used in the study roughly, and here basically were our rough possibilities for connecting north and south. And the question now was whether the decoupling, the lack of correlation in weather between here and here would be enough to improve upon the situation that we would have if we just connected Germany and France and maybe Germany and Spain, if that's possible at all. And of course, we assume here complete frictionless in politics. We just say, that's possible, and let deal others with the implementation. But we thought it would be important just to find out, does it have value in case it's possible? And then we can think about whether we should try to do it. And so this is really just a maximum feasibility study. And again, nothing in this graph is like fixed. There is not predetermined that there will be a certain power link here. It's just part of the optimization to determine how much is the optimal linkage. So in which mix of renewables, also which kind of renewables would be built is not set up before. It's all part of the optimization. And here you can see now, because it's the most graphic result, 3 weeks of power generation in the EU, so in the northern countries, for the optimal mix that we obtained. So in bright yellow, you see the only non-renewable source. So these are the 5% of emissions that were still allowed and which are in part responsible for that we don't need giant storage. Here on the lower graph, you can see the aggregated level of power or electricity storage in Europe. You can see this is like 2 terawatt hours total capacity. And as far as I remember, we didn't have any additional storage installed in the study compared to today. So I think only what was available in the Alps and the northern part of Europe was enough to cover everything. Here, the dark areas show you when the storage is used. And in the big blue areas, you see wind, which is our bulk electricity in this scenario. And in Europe, you see small shares of photovoltaics used as well. And then you see this large area, which is import from the southern countries, which are not shown here. They are shown in this graph. And here you can see in black is the demand. And you can see they are using big capacities of installed wind power, mainly onshore. Then also huge capacities of photovoltaics and a little bit of concentrating solar power, which is used to be able to also cover the nights. And yeah, they also have storage, but quite moderate. Actually, they are always oversupplying their own demand. And here in those pink areas, you also see a surplus which occurs in this scenario. But of course, as it was asked to give the cost minimum, not the maximum integration scenario, some surplus was to be expected. So under these conditions, we just obtained that it would be the cost minimal solution to strongly couple. So just to go back, like this is like equivalent to, I think it was 18% of whole European demand would be imported from the southern countries, just because their full load hours of renewables, mainly wind, are so much better than everything we have up there. Plus the decoupling between Northern Africa and Europe was good enough. Yeah, here you can see again the annual fuel mix for the whole region. You can see that basically half of the energy in that scenario is coming from onshore wind, a little bit of offshore wind, some PV, a little bit of concentrating solar power, and chunks of hydro and biomass. And this is basically the regulation that we assume from gas power plants. I'm open for questions still. It's so silent.
You know, if I'm thinking about this,
Yes.
the first thing that comes to my mind is that if I were a terrorist sitting here and I was thinking about long transmission wires going across, for example, Libya, man, could we just bring Europe to its knees like that? You know?
As I said, politics were not part of that study. And I think
I don't think this is going to ever happen.
It's
because there's just no way that those guys who are not too keen on us guys aren't going to say, well, geez, all I got to take is one of my bombs that I set off every day in Baghdad and, you know, stick a few of them along the pylons that are over hundreds of miles, and, you know, I assume that we'll be in the situation of blackouts pretty easily. And all that investment, all that energy investment will go down the toilet. Any other good idea?
so.
Okay, please.
I'm not sure I can answer within the constraints of my method here. So yeah, you could add stochastics, for example, and have a reliability criterion. I did something like this in my own PhD thesis, but would basically increase the cost of the systems. Basically, the more interconnectors you want to be able to lose before having a blackout. So it's basically it would just increase your costs, because instead of like maybe only 3 interconnectors, you would need 5, so that the cost of a terrorist attack will increase. But yeah, it's a numbers game. So
What does the word autarky mean?
What?
About the middle of that slide. Start on a medium.
Independence, self-sufficiency, independence from an it was a
It's altruism.
Will you Germans please decide on the definition of autarky?
okay. So
There's complexity and autarky, that's too much. Discuss for this evening. Sorry. Please, just
Okay.
go on hand.
So to now just get a step back and what were the common observations? Because actually we summarized those 3 papers, or some more papers, in a recently published synthesis paper where we basically reflected upon the results. May I just finish with this slide and then we continue with the discussion. And basically what we were seeing across all these studies is like sector coupling helps. There's another PhD study, PhD thesis, which was recently basically a continuation of the German slides I showed you, where the heat sector was included, and the need for electricity storage basically plummeted down as soon as you allowed large-scale power-to-heat usage, because then all those surplus could be relatively easy integrated in large-scale district heating systems, which are quite common, I could say, in larger cities. And as we go up in the scale and the, let's say, in the amount of vision that we allow in politic vision, or the amount of collaboration that we assume and frictionlessness of implementation, we are able to unlock more synergies technically. And of course, the problem of implementation remains open, but at least maybe there's something to keep in mind when thinking about the feasibility of current measures. And now to make one step further, because I've thought too much about optimization models, because in the end, everything just boils down to give me your limits. What are you willing to assume for how much renewables you may build up somewhere? What are your costs? And especially what is your objective function? Because in all those studies right now, we just went for minimum cost solutions. But instead of minimum cost, you also could minimize for something else, or even a mixture of stuff. And if here just in this graph, if you visualize Z1 and Z2 as a subset of 2 of arbitrary many goals, and you just tell me in which direction your optimum is, which basically you could visualize with this arrow, those models could basically tell you where your boundary of feasible solutions lies. So if you want to introduce, so depending on how visionary you are, basically your boundary shifts in place, and depending on your goals, the location of your optimum solution varies. But in the end, it's just a matter of your assumptions and the priorities of your goals, which tell you what is the boundary of what you can achieve. And of course, the real implementable solution will never lie on that boundary. Of course, we always have friction. We have institutions, we have protests, we have inner conflicts, but at least we can establish what is the margin or the boundary of feasibility. And this is, I think, what we can do with such models, which some might consider daydreaming, but maybe it's more important to say this is definitely something we cannot achieve, so that we can discard stuff which really is daydreaming and instead focus on areas where we can really select from a number of solutions that we might be able to achieve. And yeah, that's it. Yeah, this is just the same in more color. So I think I'll open the floor for discussion, for further discussion.
Yeah.